Okay, so let's continue with the last presentation. Now I ask Bhupendra Mishra to turn on your video and please be prepared and launch your presentation.
Hello.
About global numerical simulations of geometrically thin accretion disks. And this is a 45-minute talk, right?
I hope so, yeah.
Okay, so please, the floor is yours.
Yeah, okay, thank you. Thank you for organizers, and I hope I'm awake because it's early morning here. So I will be talking about a series of global numerical simulations of geometrically thin accretion disk. The idea here is to address, try to address at least two major problems. The one is about the stability of these geometrically thin radiation pressure dominated accretion disks. And the second one is probably far in future, that how to explain spectral state transitions in black hole X-ray binaries. So this work was done in collaboration with Vlodek, Chris Fragel, Mitch Begelman, and Phil Armitage. The outline is pretty simple here. I'm going to address this major problem, which I just mentioned, and a series of 3D global numerical simulations of thin disks. And something interesting we found recently are the spirals in our geometrically thin accretion disk simulations of strongly magnetized flows. A very simple sketch that what accretion disk we are interested. So imagine there is a black hole binary system, and there's a companion star, and then there is a black hole, and it's accreting and circularizing the matter from the donor star and forming a disk structure. Now we are interested very close to the black hole. Let's call it, say, this bluish region probably. But this is a very small scale study in the sense that we cannot fit the entire system like this in a numerical simulation at the moment. So the idea is that we assume that the disk has been already formed. We initialize it in our numerical setup and then see what how the dynamics behaves in different magnetic field configurations, radiation, and the initial configurations of the disk. But there are major challenges. So the physics of accretion disk itself is one of the challenges that you have to take care of, say, thermal properties and also the interaction of these thermal flows with the magnetic field and radiation. If we are very close to the black hole, the conditions are extreme in the sense that your Newtonian physics will not work, and you have to take into account the general relativistic effects. Other biggest challenge is that we cannot have a laboratory experiment where we can design these experiments and understand what's going on very close to the black hole. So there are three ways probably that we can attack these problems. One is simply analytic models. Second one is an approach which is combination of, say, analytic model plus supercomputing models. The third one is purely observational, where at the end we have to compare our theoretical models with observations. So probably you all are familiar, but I will just briefly mention the different types of accretion disk models currently available. One is geometrically thin disk, which is my interest at the moment. And then there are slim disks, and then the geometrically thick flows. Geometrically thin disks and slim disks have similar, say, both of them are optically thick flows. The difference is that one is advection dominated. The geometrically thin disks are not advection dominated. The geometrically thick flows are broadly studied, and they are much easier to simulate compared to geometrically thin or slim disks. What we are coming up to advocate that in future, geometrically thin disks might be replaced by elevated or puffy disk models, which they were also studied, and we recently simulated one model similar to that. The problem we are interested, a bigger picture of the problem is that how these different spectral states of the accretion disk occur in a black hole X-ray binary, low mass black hole X-ray binary. So the right-hand side plot is actually a sketch that showing how over a time, accretion disk around a black hole evolves for low mass X-ray binary systems. So the stage A is called quiescence. So the horizontal axis here is hardness, X-ray hardness, and the y-axis is luminosity or say intensity. The A stage is like say it's called quiescence, which means it's a hard state, but also very low luminosity. But as it evolves, it reaches to higher luminosities, and then still it's in hard state. It's called state B, and then it comes towards a more complicated state that we are trying to understand, geometrically thin, say it's called high soft state. Then there are various things that the jet are present until this say B region, but they turn off at somewhere in between the C and B region. And then it follows this pattern also called hysteresis plot, because it keeps following that over a time period of a few days to a few months, depending on the source. So the trouble of numerical simulations is that the time scale we have in our global models is way much smaller compared to this entire process of say 1 day or 1 month time scale. So it's still understanding the spectral state transition is probably far in future when we have more computing power. But there could be one trick that you simulate in a transition region and trigger it artificially by injecting some mass from the outer boundary or some other ways. The one way that Mitch has been advocating using his theoretical model, it's not yet studied numerically, it's an intuitive model. So in the lower right corner, you see a black dot, which is a black hole, and then there's this elliptical shape that's the inner region of a hot disk, and then it's followed by a thin disk at the outer region. Now the idea of this model is, imagine that there is a loop of magnetic field which is at this transition region, and there are various loops going back and forth from this transition region. We also know that geometrically thin disks are prone to diffuse magnetic field outwards. They tend to not let the magnetic field advect in. So the outer part is diffusing the magnetic field line outwards, but the inner part, which is advection dominated, is dragging the field inside. So what happens that there is a separation of this magnetic field loop, and if it keeps happening, the idea is that it will produce a large scale magnetic field inner part, and that could support the puffiness of the disk. So this is yet to test. It's still an intuitive idea. What we have been trying that simulating the global models of the geometrically thin accretion disks since my PhD work with Lodek. So quickly, the Shakrasane model is that you have 3 different regions. The innermost region is radiation pressure dominated, and then the B and C are gas pressure dominated. What Shakrasane proposed that the stress, which is a vertically integrated stress DR phi, and the vertically integrated total pressure. Okay, so that's defined as the alpha viscosity prescription, which probably comes from some sort of magnetic field driving turbulence in accretion disks. But soon after this discovery paper, or say groundbreaking paper, they also found that these particular inner regions of this Shakrasane model are thermally and also viscously unstable. So this created a debate, and people have been trying to simulate it in various ways, say local shearing box simulations, and then followed by a global simulation that I did in thesis project. So this is a very initial setup of how we are initializing our global model. We are doing just 90° in phi in order to save computing time. The boundary conditions are periodic in phi, and in the inner part, it's outflow boundary condition, meaning the plasma or the flow can go into the black hole. The outer boundaries are constantly fed with, say, a fixed value of m dot, which means that the very last active cell of this numerical domain are constantly replaced by the ghost cell value next to it. So it's like feeding the matter from the outer boundary at a constant rate. We did it in a cylindrical coordinate system. The idea was to have a much higher resolution at the disk midplane by using a logarithmic grid in vertical direction and also in the radial direction. Then we had a set of models that low resolution and high resolution runs with the different grid cells in R, G, and 5, R, phi, and G in this case. But since we cannot say just based on the one radius and pressure dominated simulation that the disk is, say, thermally unstable, we also tested it with a gas pressure dominated model to confirm that what we are seeing is not an artifact, numerical artifact, and then the gas pressure dominated disk should be stable. So these are the 4 simulations we started, and we found that radius and pressure dominated disks collapse, thermally collapse, and the gas pressure dominated disks are still stable. The units are really simple, also in gravitational radii for length, and the units are, say, Rg over C. The black hole mass we are deciding here is 6.62 solar mass, which is not any magic number, but we are following the local sharing box simulations performed in the last decade or so to make a close comparison with those models. So the way we set up is a thin slab of this. So this is not yet a Shakra-Sunyaev model, like profile-wise, density-wise. And we have a constant height slab along radial direction, and it follows a vertical profile described here from Reynolds and Miller paper. So the domain size, you know, see, it's not extremely large domain. We are very close to the black hole and trying to understand in the very close to the black hole what happens to this particular model. The initial setup, the hydrodynamical setup, is also seeded with a weak magnetic field. When I say weak, I mean it's seeded with the 0 net flux. So even if the beta is 10 here, the field lines, sorry, the magnetic field strength is weak. And in that case, you have this small loops of magnetic field going along the disk and also in entire direction, in the phi direction. Now we include the radiator transfer self-consistently, but with an approximation, this M1 closure, probably all familiar with. So the opacities are treated electron scattering and absorption and thermal comptonization. And just to remind, these are optically thick flows. So we start with I will start with the gas pressure dominated disk results. So what you are seeing here is the evolution of the density with time. The time is given again in the units of GM over C cube. What you see here that at a very inner part, the disk remains stable and it's not, say, thermally collapsing or what we have been finding in the radius and pressure dominated disk case. The outer part certainly shows that it's collapsing, but that's because the time scale for magnetorotational instability to grow in that larger radii is much larger compared to what we have been running here. So over the time, this will take back into the stable state. So quantitatively, to compare the heating rate and the cooling rate, you see this plot here. So this vertical axis here is time, and the horizontal axis here is radius. What you are seeing on the color bar is the ratio of heating rate to the cooling rate, and it's plotted in log. So most of the simulation is showing a value close to 0, meaning that the disk is thermally stable, the heating and cooling rate are in equilibrium. Now, if we see what happens to the radiation pressure dominated disk case. And if you go back to those stability curves, what we are finding that when you are starting it, say this is a called S curve, where you don't see S actually, because you will have to make this upper branch also, which will correspond to slim disks and hot advection dominated disks. So what the horizontal branch here is the innermost region of Shakra-Sinyan disk. And this stable branch is like, say, the outer regions, region B in this case, what I was talking about. So this is at a fixed radius, and for a fixed value of alpha, and the horizontal axis is showing the surface density. Now the philosophical question here is, to decide what value of alpha you want, you have to rely on MHD or GRMHD model. But in order to initialize your setup, you have to decide where do you want to be with your T naught, like the one here, the smallest blue dot. So once we performed these GRMHD models, we found that alpha is 0.02. We overplotted this stability curve on top of these, say, blue dots, where we find the evolution of our GRMHD model. So you immediately notice that our T naught is below the horizontal branch, meaning that probably that when we started the simulation, it was not on this horizontal line. So that means, in other words, I wanted to say that it could have been that possibly it will not collapse, but it will evaporate, like the heating will dominate and it will vertically expand. That didn't happen. It kept collapsing towards the stable branch. And I will show another slide where we check for different initial setups, and we found that it's always collapsing. So this is what happens for the radiation pressure dominated disk. You see, initially it was expanding, and that's the time when the magnetorotational instability develops, the heating is developing, but soon the cooling starts to dominate and the disk collapses to a very thin single cell height, and we cannot resolve it any further. So this is a problem with the radiation pressure dominated disk model when you do not have a way to stabilize it. So it will collapse to a thin disk. So this is again, set of snapshots to show that on the left-hand side, you have the initial profile of density, temperature, and the ratio of radiation to gas pressure. And this is again showing the RG slice of these simulations. So eventually you see that the disk has collapsed in the upper rightmost plot, and the temperature is also decreasing since it was cooling. However, the radiation pressure is still dominated over the gas pressure. So now if we see that what's the disk height look like. So these are again the plots where the vertical axis is showing the time and the horizontal axis is showing the cylindrical radii. This dashed black curve is the local orbital period at the time when the MRI starts to develop, approximately this time. So it starts to heat up the disk, and this color bar, if you notice, the red region here is showing the higher values. So the red region is telling that the disk height is increasing, but soon the disk height starts to decrease and it collapses to a very thin disk. So this white curve here is the local cooling time. And the reason we needed a higher resolution run was to resolve the MRI better in the phi direction compared to the low resolution run on the right-hand side. But both of them showed qualitatively similar behavior, that the disk is collapsing into a very thin disk. And the heating and cooling rate ratio for this particular, say, radiation pressure dominated high resolution run is again the similar plot like I was showing for the gas pressure dominated case. You see the dominant region here is blue, which means the color bar is showing we are in the cooling rate dominated regime here in this radiation pressure dominated case. So this was first global GRMHD model with radiation, confirming that thermally the radiation pressure dominated disks are thermally unstable, and what has been predicted by local shearing box models is we are in agreement with that. And this is like a side-by-side comparison that the stable disks have a balanced heating and cooling rate, and the radiation pressure dominated disks have dominant cooling. The other instability, which was also predicted for these models, is viscous instability. And the idea is that when you have a diffusion equation, if your diffusion coefficient is negative, then you will start to accumulate the matter into high density clumps. And this was called also Lightman-Erdel instability, which was generalized into the general relativistic regime by Modresky and Bojana. What we are finding is similar to what has been predicted for the viscous instability. So on this zoom plot of the very inner part, you see a ring here. So just to clarify that this simulation was done with a phi of 90 degree. So I just replicated it to show the entire ring. So if you see just 90 degree, you wouldn't see the entire ring. It's still a arc, this bright color, say high density arc in this 90 degree view, but I replicated it to show the entire ring. Now, if we compare it with, say, the theory of this viscous instability from Lightman-Erdel paper, the idea is that the vertical integrated torque and surface density should be anti-correlated. So on this right panel where you see this, where you see the high density, high surface density vertical structure at around 3,500 and radius of 8, that's coinciding with this, say, in this low torque region. So the idea is that the theory of viscous instability is that vertically integrated torque will be anti-correlated to the surface density. And could it be that we have made our models way too complicated, that we have added radiation and everything and not able to understand what's going on? So we turned off the magnetic field, and let's see what happens to actually just Shakuros in a model with alpha viscosity and see what happens to these initial profiles in a 2D GRHD model, this GR hydrodynamical model. So again, these are the different initial configurations like you are seeing here with the different luminosity. So this one was say 1%, and say 0.1%, then 1%, 3%, and then 10% Eddington luminosity. What you are seeing with these different colors, like where we started our initial setup. So if we start it at the horizontal line on the left-hand side plot, so these are plots at two different radii, at radius of 10 and 15, I believe. But what you see here that all the initial models we set up, they collapse to towards the gas pressure dominated region. So this cyan color, which was started even above the horizontal branch, still it collapsed to the lower gas pressure dominated branch. The other interesting thing you might notice that whatever we defined as a stable branch for the gas pressure dominated branch, analytically, and it's not exactly that, but the simulations are finding another slightly lower temperature stable gas pressure dominated branch. So this was done to understand that we did not miss anything in the more complicated model. So the question is, what can stabilize these disks? So the first attempt in a global simulation was by Oleg Sadowski, that if you start with a magnetic field configuration which has enough radial magnetic field component that can be dragged and produce large toroidal field and could stabilize the disk. So these plots are again showing, say, cooling rate and the heating rate. And then it's shown that when you have a quadrupole magnetic field configuration of this paper, you have heating and cooling almost balanced. So the question is, are these strong magnetic fields really the key to stabilize these accretion disk models? And we further studied it based on one study that shows if you seed it with a net vertical field, meaning poloidal field where the net flux is non-zero, then you might produce a large toroidal field and also elevate the disks and stabilize the disks. So this snapshot is from a local shearing box simulation. So from top to bottom, you are seeing the beta, which is actually the ratio of gas pressure to magnetic pressure. So if you keep increasing the magnetic field strength, you see that the beta 5, 4, 3, 2, 1, meaning that if you have a net vertical field, which is say this last one, say the strongest field configuration, the black one, it reaches to a magnetic field, the beta parameter of 0.2 or 0.25, meaning that you can produce a large magnetic field if you seed it with a net vertical magnetic field. So we started this global model to seed the disk with a net vertical field, and that made things more complicated actually, in the sense that when you seed the thin disks with net vertical field, you have a big trouble of inner boundary conditions that will act in a way that like create large winds, and that would evacuate the inner parts and create a very small time step. And also we can have many technical problems when you start with the vertical field configuration. So in order to resolve these disks, we had a static mesh refinement. So this was a full 3D global model with 360 degrees. So you have to resolve the disk. So we had effectively 2048 times 1024 times 1024 cells effectively to resolve this particular model. We are in the strongly magnetized regime. So the leftmost one here is weakly magnetized case, and the rightmost one is magnetically arrested disk. But what we are interested in is the MR-active one, the middle region, strongly magnetized flow. What we found was very intriguing. So on the left-hand plot, what you are seeing is phi averaged density on the left half and the radial velocity on the right half. And the blue region here is showing the flow is moving inwards. The red one is showing it's moving outwards. The left-hand side is again, say, just density. These green curves are showing magnetic field streamlines, or just say magnetic field lines. The very intriguing feature was that the midplane is not accreting. The accreting is primarily happening on this pinched in region of the blue region, which is, say, we call surface accretion. The midplanes are showing outflows, which is not actually very surprising. What Vlodek is also here, and he has also worked on it, and they also found this backflows at the midplane of the disk. The right-hand side plot is showing that the ratio of gas to magnetic pressure. We start with, say, beta of 1,000, 300, and 100 in the initial model. And when you have large vertical field, large scale vertical field, and the Keplerian flow, then it drags the magnetic field in the phi direction and produces a large toroidal field. So what we are comparing here for the total magnetic pressure. So you see, we started with, say, beta 100. It reaches to a beta of approximately 1 or 3 for the beta 100 case. For beta of 1,000 case, we start with 1,000, but it reaches to beta of 100 at the midplane. But look at the surface regions, like, say, the higher altitude regions, the beta is even smaller. So we are able to produce large magnetic field, which eventually creates an elevated disk profile because the accretion is primarily happening at GOR of 0.3. The further analysis was that what happens, what's driving the accretion here? So certainly it's Maxwell stress dominated for the total stress profile. Now the upper left plot is showing the total Maxwell stress. What you are seeing that the dominant accretion is happening in this, say, peaks, like say the green peaks here at around say 0.2 or somewhere around 0.15. Now, if you decompose that total Maxwell stress into say turbulent component and the coherent component, what we are finding from the upper right corner plot that the accreting regions have a coherent magnetic field dominated Maxwell stress component, whereas the mid plane is more turbulence dominated. So that's something new and interesting. Then we also computed having this global model, we computed alpha profile to compare it with the local shearing box models and the simulations we did before. So the alpha here is on the left-hand side plot, is showing the horizontal axis is again initial beta, that at what beta the simulation was started, and the vertical axis is showing the alpha, total alpha. So you are seeing that alpha for say beta of 100 case is about or maybe 3 or 4. And it's coinciding with the local shearing box simulations. Now, if you normalize your alpha with the magnetic pressure, then it's pretty much like a horizontal line. So alpha doesn't change by changing the beta. So just to make it clear, the alpha here is total alpha, meaning taking into account the total stress component, not just the turbulent component, because then alpha should not be larger than 1. What we are comparing it in the right-hand side plot, the GRMHD model we simulated, that was giving alpha 0.02 in our radiation pressure dominated model. So what we are claiming that we need much higher values of alpha to stabilize these disks, and also the stronger magnetic field strength to create these puffiness or elevated disks. So this is again a comparison of what Deborah found from our simulations, that they have kind of similar structure for magnetic field pinching in. Certainly, I'm not sure about the accreting region. I think that Deborah's paper did not show surface accretion like we are seeing, but the initial setups are slightly different in both of models. The other interesting feature we found that when you start with a very strong magnetic field, since it was a fully 3D model, we could see these large scale spiral structures. So these are found in the nature in general, but what we are finding in our global simulation, I should probably fast forward it to show that. So what you are seeing here is a mid-plane slice of this 3D model with a beta of 100, the density evolution. So you see that there's a large density contrast, like sometimes factor 5 or even an order of magnitude between these spiral structures and this high density structure. So this was not seen in the weakly magnetized case for beta of 1000, but when we have beta of 300, 150, these spiral structures start to get more and more prominent. Now, if we try to fit these structures, the spiral structure, we can actually fit that with the logarithmic spiral. And what we find that the pitch angle of this spiral is inversely proportional to initial beta. So on the left-hand side plot, you are seeing, again, this slice for the phi component of magnetic field. And this black curve is a fit with, say, B of 0.3. Another interesting thing you might notice that the polarity of magnetic field is also changing. So the red to blue is positive to negative, meaning that there must be, say, current sheets going along these large spiral structures. So this is something we are still trying to understand. And I think this was just to show the density contrast, but I have already mentioned it. So the idea is that the density is confined in this edge of the spiral region. So if you subtract off, this plot is subtracting off the phi average density and then normalize it with the phi average density. So you see that most of the density is concentrated on this surface of the spiral structure, which is coinciding with the current sheets where the field lines are flipping the sign. Now, to make it more clear, here is this 1D plot. So upper panel here is showing density. I started with a time of 33. The units here for the time are local orbital period at radius of 1, because this is a Newtonian MHD model. Now, the lower panel here is BR and B5. Now you see that this density peak, which I was just trying to show, coinciding with this intersection of this red and green curve. And then it keeps following for 50 orbital periods, the last time snapshot we have for this run. So this is interesting that these particular high density regions are confined with these current sheet regions. And these, this is another movie, I guess. So when we say the height of these spirals, they are not just confined to the midplane, they have a vertical structure, meaning they look like icebergs on accretion disk. So this plot is showing at a fixed radii, the vertical axis is showing the height of the disk, and this is a phi direction. So at a fixed radii, if you keep going in phi direction, you will encounter this kind of large vertical structures, which are actually these high density spiral structures and this high density wall at the edge of these spirals. So those are structures we are finding and we are trying to understand. So my summary slide here is that probably to stabilize unstable Shakra-Sinai model, we need elevated or puffy disks, and also large values of alpha viscosity parameter, which we find from these global MHD and GRMHD models. So with that, I would say thank you.
Thank you very much, Bhupendra. This was very interesting talk and beautiful simulations. Actually, first question that comes immediately to my mind is that advection is a mechanism that is known to stabilize the radiation pressure dominated disks. For a long time, we studied this with Bożena in a series of papers of these unstable disks. So why don't you include this into your models?
That's a good question. So once we have, so that's a question that we are actually following up these simulations with a fully radiative GRMHD model with the net flux to understand if these vertical field and the net flux creates elevated disks, meaning that the disk height will be much larger, then they might get advection dominated or at least allow some advection. And once we have the radiation there, we might understand the question you are asking. So this one was without radiation. I should have mentioned that the MHD model I was talking about with the net flux was first stage of our study that we excluded radiative transfer. So the cooling was included artificially. It's instantaneous cooling at each cylindrical radii by maintaining each ring into isothermal state. So that's a good question. I hope we understand it from the simulations I'm running now.
More questions. I invite people to raise your hand or take the microphone and ask. I see Wodek wants to ask question, right?
That's so much. Great talk, Bhupendra. If I may comment on your question, I'm not sure I fully understood it, because in the numerical simulation, advection obviously is included. So, you know, it is what it is.
Well, it was not mentioned and neither shown on the stability curves, which he was presenting.
Well, the stability curves are analytic, right?
Yeah,
so,
I know, but
the
somehow,
the simulation is the result. So Bhupendra showed that the thin disk is unstable when you simulate it, and then the simulation advection is present.
So that was a bit confusing for me, maybe.
Okay.
But okay.
Right. So we certainly allow advection if there is, but probably these disks were not elevated or puffed up because they were weakly magnetized. So probably if we have much larger disk thickness, probably the advection will dominate, maybe. So we do not stop if it wants to advect in.
Maciek, please ask.
To add to this discussion, I understand, please feel free to just tell me, go read the paper, but I understand there must be some limit when advection starts being important. And the disks, Bhupendra, you are simulating, I understand those are this sort of mildly, what's the mass accretion rate? It's not a huge mass accretion rate, right?
It's say 10%, Eddington.
Right. So would that be enough to have effect on stability? I don't know what is this. Is there a special slim disk equation of influence of advection when it is sufficient to stabilize the disk? But I understand there must be some point when it kicks in. Right?
Okay, so there is one concern. Okay, so what we are finding that the disks are being thermally collapsed, right? So they are cooling, right? We do not want an advection acting on top of it so that there is more radiation advected in. So if there is advection dominated, if the advection dominates, we will be in trouble actually, because we are not finding the disks which are expanding or evaporating. They are collapsing. So we want the radiation to be there. So if I understood correctly, we need probably not to have advection to stabilize the disks.
I think if I may jump in here too, I would. I think Maciek has a good point that at high mass accretion rate there is advection and the disks are stable, but they are no longer thin, I guess. So it's outside the scope of your talk.
Right, those are slim disks.
It's not, well, slim is just a name, but they are thicker. They just become thicker when you go to high accretion rates. That's all.
Okay, I see Deborah wanted to ask question.
Okay, thank you. I wanted to comment on the advection problem and the stability. It was main goal of Oleg Sadowski paper, 2016. Bhupendra showed that for a stable thin disk or finished disk solution, you need a magnetic field to stabilize that. With weak magnetic field, the disk is not stable even with advection and quite high mass accretion rate, about 0.8 Eddington. So he showed that not only advection works in a slim disk or a thin disk simulations.
Okay, thank you, Deborah, for comment. Are there other questions, comments, not only about advection, but any other to the speaker? I can't see now, so
I have
yes, please.
Okay, I know the simulation is Newtonian, but you show us the plot of torque, and is there any? Is it a average of from the simulation, or is it a snapshot? My question is if there is some like border when the torque is changing, which can be something like ISCO in a GR, if you know what I mean. But if there is a border, like an inner border of the disk.
Yep. So
because on the video you showed, there was something like in a region when everything just fall in, and it looks.
I checked the So this is at a fixed radius, but time averaged for 5 orbital periods. And I also checked it for different radii, but it looked same. So even if we do radially averaged stress profile, it looked that coherent component dominates on the accreting regions. And that would be consistent with the plot here. But I'm waiting for the GR calculations we are running now for the same magnetic field configuration.
Okay, thank you.
Thank you. Any more comments, questions? If not, let's thank the speaker again.